flipped classroom video for Further Maths Unit 2, Goodness of Fit with chi-square. Goodness of fit is concerned with measuring how well an observed frequency distribution fits a known distribution. Suppose that you throw a dice 120 times and record the results below. So the face 1 has appeared 23 times, the face 2 15 times, and so on. If the dice was unbiased, we should have equal results for each face, as each number has equal probability of occurring, and we'd have 1/6 probability for each face occurring. This is an example of a discrete uniform distribution. Uniform, they're all the same. The probabilities are all the same. So if we multiply those with 120, which is the number of throws we've had, then our expected frequency should be 20 each. Now, we need to set up a hypothesis, and the null hypothesis would be that there is no difference between the observed frequency and the theoretical distribution, while the alternative hypothesis would be that there is a difference between the observed frequency and the theoretical distribution. Then, so we are going to use a goodness of fit testing using these values. So we've got an observed set of frequencies and we have an expected set of frequencies. And our hypothesis was that there was no difference in the observed and the theoretical distribution, and H1 was that there is a difference between them. So as a measure of the size of these differences, we're going to sum the squares of the differences and divide by the expectation, then sum. Yeah, so square the difference, divide by the expectation, then sum everything we've got. And that is our test statistic of x squared, which is going to be our estimate for chi-square. Now O is the observed frequency and E is the expected frequency, and the sum of these frequencies is n, so the total amount of trials. We're squaring so that there's no negative values, so it doesn't matter which way you're taking them away. We can also change this formula to give us this formula. Prove it on the next slide, and these are not given to you. So if we prove this, take the middle term there, square the bracket, then divide each one by E and take the sum in. So you've got the sum of O squared over E. The E is cancelled here, so we've got twice the sum of O, and one of these is cancelled here, so we've got plus the sum of E. Now as the sum of O and the sum of E are the same, as they're the number of trials, so minus twice of them plus once gives minus once, and that is equal to n. So our two formulas are the same. So back to our frequencies. There's the observed and there's the theoretical, the expected. So if we take them away, square them, divide by E, add them up, and we get 3.4. So that is an estimate for chi-square distribution. The x squared, the test statistics, is approximated well by the chi-square distribution as long as the total frequency n should be at least 50 and that none of the expectant frequencies falls below 5. What we do then is combine or pool adjacent frequencies to make sure the values are 5 or more. And this is the table we're going to use, table 6, which gives percentage points of the chi-squared distribution. So our number of degrees of freedom, which we are going to use down the left-hand side here, would be the number of cells minus the number of constraints. When the parameter is known, you have n minus 1 degrees of freedom in your choice of cells. In our example, there are 6 faces, So 5 free choices as the last. Once you distributed 5 of them, the last one must complete the sum to get the total. So there are n minus 1 choices of cells. So, when testing for large discrepancies between observed and expected frequencies, the critical region is always in the upper tail of the chi-square distribution. Extremely small values of the test statistic, chi-squared, are very unlikely, or x-squared, very unlikely to occur, as this would mean that the observed and the expected frequencies are suspiciously close together. So back to our example, we've got that x squared is 3.4. So the table we need is table 6. We've got 6 faces, therefore 6 minus 1, 5 degrees of freedom. We're going to test at 5% significance level, so it's the tail end we're looking for, so we're looking at 0.95. Therefore, chi-squared is going to be 11.070. So that's our expected value for the critical region. So the critical region is that or above. Our value is not within that, so we are going to keep H0. There is no difference between the observed and the theoretical distribution. So it's an unbiased dice. Tested the binomial model. There must be a fixed number of trials in each observation. The trials must be independent. The trials must have only 2 outcomes, success or failure, and the probability of success is constant. So binomial model next. So the expected value would be the probability for a binomial model, and then multiply by the number of trials. So the binomial distribution has 2 parameters, n and p. We have the usual restrictions that the expected frequency need to have the same total as the observed frequencies. So being as p is going to be known in our situation, then our degrees of freedom nu is the number of cells minus 1. So n minus 1 would be the degrees of freedom. So our example, the data in the table are thought to be modeled by the binomial b with n is 10 and p is 0.2. Find the expected values and conduct a test to see if this is a good model. Use a 5% significance level. So we have a frequency. There's the values of x. So we set up our hypothesis, being there's no difference in the observed and the theoretical, against that there is a difference between the observed and the theoretical distribution. Add the frequency and we get 100, so it's been there were 100 trials. Each probability has to be worked out. You're not given anything yet. So the probability of x is 0, should be 10, choose 0, 0.2 to the power 0, and 0.8 to the power 10, giving us that. Work through them all, and we get these values for the probability. We need to multiply those by 100 to get our expected frequency. So we should get, for x is 0, so that multiplied by 100 would be 10.74. Probability x is 1 multiplied by 100 would be 26.84, and so on. So those are our expected frequencies. Don't round up too much here. We need to pool the results, being as we can't have values of the expected frequencies less than 5, so we need to pool these results. Even if I add the 5, 6, 7 and 8, I still wouldn't get 5, so I need to add them to the 4, and then we get 12.09 for the expected value for 4 and above. and add the observed frequencies as well, and I get 15. So I have those values for the expected frequencies, those for the observed at the top, expected underneath. We're going to use the other formula now. So squaring the O and dividing by the E and then adding up, I'm getting that answer. Take away the N and I get 1.1545 for my test statistic. Looking up table 6, 5% significant level, P was given, not calculated, so our degrees of freedom is 5 boxes, take away 1, which is 4. In the table, 4 degrees of freedom, 0.95 as our significance level. So above that, that's the critical value. Above that is my critical region. My value is well below that, so it's not in the critical region. So I'm keeping the binomial as a suitable model for the distribution. Testing a Poisson distribution as a model. So the conditions in which Poisson distribution is likely to arise are the n events occur independently of each other. The events occur at a constant rate in the sense that the mean number in an interval is proportional to the length of the interval, and the mean and the variance are equal. And our formula for working out the probability of x equal to each little x is e to the minus lambda to the power x over x factorial, and we'd multiply that by n to get the frequency of each value. The Poisson distribution has one parameter, lambda, which is known, so our degrees of freedom would be the number of cells, take away 1. An example of this, the number of complaints received in a day at branches in a major chain of high street banks is given in the table below. It is hypothesized that the number of complaints is modelled by a Poisson distribution with mean 0.7. Test this hypothesis at the 5% level. So we need to set up our hypothesis that the null hypothesis is that the Poisson distribution is a suitable model with that value of lambda, and against the cause cannot be modelled by a Poisson distribution. So we need to work out the probability of each value. So generally, the probability of each x equal to little x is e to the minus 0.7 multiplied by 0.7 to the power x over x factorial. So for x is 0, we get that value. X is 1, 2, 3. Our sum is 461 and 4. So 4, well, I could work that one out or just wait until I work out the cells and then make them add up to 461. So either you work it out, the probability, or you wait and work out each one. So multiply each of our probabilities by 461 and I get 228.9 for the probability of x is 0, 160.2 for x is 56.1 for x is 2, x is 3, I've got that value, x is 4 or more. Now I needed them to add up to 461, so I could have worked that out and multiplied by 461, or I could have just added them and make them equal to 461. Remember, don't round up our expected values. This is less than 5, so we need to pool the last two columns. So I'm getting greater than or equal to 3 with 12 as my observed value and 19.8 as my expected value. I can work out the test statistics, so the difference squared divided by the expected value and add them up, and I get 10.86 as my test statistic. Looking that up in the table, 5%, 4 columns, Therefore 3 is my degrees of freedom. In the table 0.95 with 3 degrees of freedom, I got my test statistic. No, my critical value is 7.815. So the critical region is above that. Our value is within the critical region, so I'm rejecting H0. The Poisson distribution is not a suitable model to use. It's not close enough. And that's the end of the video on goodness of fit. So we need to use it on uniform distribution, binomial, and Poisson.